Welcome back. In this lecture, we'll talk about blockMesh. Let me first introduce blockMesh. For example, you want to create a mesh for a channel which is rectangle. The easiest mesh is to divide all the edges along the Cartesian grid. Right? Let's say you want a final resolution along this edge, then you can create final division near that axis. In blockMesh, you can transform this to other shapes as well. For example, this particular rectangular duct is of this shape. Then also you can do the same thing, divide along the arc, and you will have a grid which you can control easily. So the benefit of blockMesh is that you always know your neighbors. For example, you have I, J, K, the index for this particular block. Then the right hand side is I plus 1, comma j, comma k, and similarly all other directions. Therefore, block mesh are preferred, and you have a much better control on the resolution. If you want to increase resolution at this part, you'll just make inclined lines like this. So this kind of mesh is also possible. Clearly, these edges spacing have a smaller length compared to these edges. These kind of manipulations are possible in block meshes. In OpenFOAM, while creating a block mesh, you should take care of two basic steps. Others are just syntax. First one is that the block numbering, to construct a block, you should have 8 vertices. These are the 8 vertices, and the numbering is also followed in a specific manner. First 0, then 1, then 2, and 3 in the counterclockwise direction, and then the vertices which are exactly opposite are numbered 4, 5, 6, 7 in the same counterclockwise direction. These are local indexing to be followed using the global index of the vertices. For example, there is another block here. It will take 5, 6, 1, 2, and then other vertices. These vertices can have any index, but they must be ordered in this following manner: 0, 1, 2, 3, 4, 5, 6, 7. So this will be clearer when we'll construct the block mesh for our geometry. In a similar manner, the edges also have a certain order. First, this edge is numbered as 0, and then all edges parallel to this edge, which is 1, 2, and 3 in a counterclockwise direction. Similarly, along the y direction are numbered. Here we'll have this one as 4, then 5, then 6, and 7. Then in the z direction, starting from here in the counterclockwise direction, 8, 9, 10, and 11. Remember, while mentioning a face, that should be a boundary, the normal should always point outward. If I want to make this particular face as a boundary, you should mention in a counterclockwise direction 2, 6, 5, and 1. If this much is clear, then we'll start with our model. So first, this is the backward facing step. We will use cyan color and create the back face of this particular block mesh. We will use red color to connect the back layer and the front layer. Since there is a step, this will not allow to create a block which does not have a domain boundary. Therefore, we have to create another block with the blue line, and then another block which is vertically bisecting the domain, and another block because we have a symmetry bounding condition at the initial part of the inlet. Now we'll see that how we can have different gradients. We need fine mesh near the walls. A naive method is that we bisect this domain into another domain and then use finer resolution towards one of the end. But this will create a lot of mesh points. So we'll also see that how we can avoid this and how do we do grading in blockMesh. Let me highlight the vertices. I will use another color to highlight the vertices. Number them starting from 0. I'll first number all the vertices in the front face and then number all other vertices in a similar manner. We know that the coordinate here is -120, -110, here 0 and 50. Similarly, along the y-axis, these are the coordinates that we have. Now we'll write a blockMeshDict which will automatically create a block mesh for our domain. So I have already copied the cavity example in this BFS block folder. If we just run blockMesh here, then the mesh that is generated will be for the cavity example. So if you look at the mesh, clearly it is the mesh for the cavity example. Now we'll edit the blockMeshDict for our example. This particular header is most important because without this, OpenFOAM will not recognize that what dictionary this is. And then there's a scale that you have to put in. In the OpenFOAM example, the backward facing step is already there. They use a different scaling, which is 0.0127. So we are going to use that particular scaling just for illustration. Because eventually we are going to use the mesh which is in that OpenFOAM example. Let's see how we can add vertices. So we'll add vertices one at a time, and these vertices should not repeat. Always make sure that these vertices are unique. For example, the first one is -120, 1, 0, and then next one is -110, 1, 0. In the similar manner, we can add all the vertices. We should number them from 0, 1 onwards so that we can create the blocks. Once all the vertices are added, let's see how we can write the blocks. In order to write the blocks, always remember that you have to follow the same indexing pattern that we have discussed. The first phase should be in such a manner that when it is written, the normal is pointing outward, which is 0, 10, 11, 1, and then the next phase should be starting from the vertex which is opposite to 0, which is 9. So starting from 9 in the same direction, 9, 19, 18 and 8. Once you have written all the blocks and remove all the boundary content, run the block mesh. Only one outer face was generated because we have not set labels to any boundaries. So it sets default face to all the outward facing boundaries. Run OpenFOAM. We'll see that the domain is created as we wanted, but the meshing is not what we expect. So now we'll see how we can set the grading so that the mesh is very fine near the step. In order to do so, we'll see that how we can use the inputs which is just next to the definition of the hex. The first value here says that what should be the division along the first axis, which is 0 to 10, and it says 20. We don't want this. We want only one element along this direction. Similarly, for all other blocks, we want just one element. Second direction is 10 to 11. Along 10 to 11, we want according to the length. Since the length is 10, therefore let's set this to 10. So similarly for next block, the length is 110, so we'll set it to 110. Next block is of length 50, so we'll set 50. Similarly for the other block. The next direction is the direction which is along the y-axis from 0 to 9 for the first block. So let's set the number of element along this according to the width. So let's set this to 80 for all the blocks. For the last block, which is the step, we'll set 10. Now running this, we'll see that now we have much finer mesh but still near the step we don't have the resolution that we want. In order to see what resolution we want, we'll use the ruler and set this to 0.0005. But we should first calculate that for the current scaling, so this value should be multiplied with the scaling. Clearly this particular resolution is not even 0.0005, and what we want is much smaller than this because we have a scaling as well. So we can see in the blockMeshDict we have a scaling of 0.0127. So if we calculate the first layer distance from the wall, this should be 0.0127 times 0.0005, which is equal to this value. Clearly this value should be much lower. Therefore we need to do some kind of grading because we cannot increase the number of divisions along the axis to get this resolution. This will increase the number of mesh element unnecessarily. Therefore we have to use grading. Simple grading says that it is equally divided along each axis. Each number is for one of the axis. For the first axis we don't want any grading because there is only one cell. For the second axis we want some kind of grading. Let's do only one kind of grading just along the z direction, which is the width of the inlet. Let's create a variable first with the name y spacing. We have to define that 50% of the edge have 50% of the cells of the total number of cells, and which has a grading expansion ratio of 100, and then the next 50% will have other 50% of the cells and will have grading in the other direction. This is how we are defining the grading for just one direction along the width of the inlet. To use this variable we just use with dollar sign, and similarly for all other blocks except the last block. So now if we run this particular script and view this in para form, we'll see that there is a grading. So 50% of the cells are below and the grading is in some particular direction, and for the other 50% it is in the opposite direction, which is what we have set. Let's say you want the grading in other direction, you can always change this. So you can go back to the blockMeshDict and then change these two values to opposite of this with 0.1 and 100, and this will change the grading to opposite direction. So again we'll run the blockMesh and reload this file. You'll see that the grading is in the opposite direction than what it was before. In order to have more advanced grading, we can do different grading to each of the edges. Since there are 12 edges, we'll have the first edge along 0 to 10, and then the next edge will be parallel to this in the counter clockwise direction, which is 1 11, then 8 18, then 9 19. So all of them we want 1 1 1 1 grading. For the next one we'll set the same thing here, again 1 1 1 1, and then for the next 4 we want this particular spacing. We are going to recreate the same kind of grading that we have created using simple grading, using edge grading. You should remove the simple grading because both of them are doing the same thing. You should not have both the things, and then rerun blockMesh. You'll see that we have the same mesh as before. Now let's go back and see how we can change the grading for a particular edge. Let's define another grading for the edge 0 9. So if we are setting something to edge 0 9, then we have to set the same thing to edge 10 19. Let's define here y space 2, and 30% of the edge will have 50% points. Then next 20% will have 20% of the points with a grading of say 2, and then the rest of 30% will have 30% of the points and will have grading say 100. Now we have to use this. In order to use this, we go in a particular edge 0, 9 is the first edge. We want y spacing 2, and for the next edge 10, 19 as well. Let's close this and run the block mesh again. We can see near the first block we have different type of grading compared to what we have on the other side. The first block have a very high reduction ratio, the second block have around negligible expansion, and the topmost block have significant expansion ratio. Using requires a lot of practice. In this tutorial we are not going to go into the details of what we can do to create good mesh. We'll take the mesh which is already there in the OpenFOAM tutorials, because if you go back and check the quality of this particular mesh using the check mesh command, you'll see that the quality failed the check mesh check. There are a lot of edges which are not aligned. There are non-orthogonality which is greater than 70. Before copying the blockMeshDict from the tutorial, we'll just show how to create labels for boundary surfaces. We'll go to the boundary. Then in order to add a label, write the name. Here we want to add inlet. And once we have added inlet, then you have to write the type, another dictionary. Then you have to write the type is patch, and then the faces which will make this particular boundary. So in order to write the face, we have to write the vertices in the order such that using the right hand thumb rule, the normal point outwards. In this case, if we select 9, 19, 10 and 0, then we'll have a normal which is pointing outwards. Let's run the block mesh again. Now here you can see that patch is created with the name inlet, and all other faces which was not declared are inside default face. You can also see inside the polymesh boundary, one label is created with the name inlet, and all other faces are in default faces. So you can assign them according to their face numbers. Let's look at the file which is already there in the OpenFOAM tutorials. There is a scale of 0.0127. There are various variables as we have also defined, followed by blocks. So here we had only 4 blocks, but here they are using 5 blocks. This followed by boundary definitions. For now, we'll just copy this particular mesh, and then we'll use this to run our simulation. We'll just replace this file, and then let's run blockMesh and look at the mesh file. So here you can see that the mesh is very fine, close to the step, and it is coarse and has a very high aspect ratio away from the step. On the other side as well, you can see that it has a very high aspect ratio. Notice that there are only 20,000 cells, which is much less than what we have got using triangulations. What is the minimum cell size created here? We'll use a ruler for that. Let's input the points. We have to multiply with the scaling factor. Let's do that. Put the value which we have just calculated. And here we can see that the mesh is very close to what we require. Learning how to create this kind of mesh requires practice. This will be done in some other course. We'll use this particular mesh for our analysis. We'll see how the results are affected for different turbulence model on this particular mesh. We have also seen that the triangulations create a lot of mesh, and the process is mostly automatic, and there are alternatives to that which is already present in OpenFOAM. So in the next lecture, we'll use Parlart LMRS model to simulate the flow over the backward facing step. Thank you.